Good morning, everyone. So in today's lecture, let's talk about tropical cyclones. So cyclones, as we have seen in the last class, cyclones are a general low pressure systems. And these low pressure systems developing anywhere. Now, based on the region, depending on the region, we identify them either as temperate cyclones or tropical cyclones. Temperate cyclones, already we have seen what exactly constitutes temperate cyclones. Okay, so now let's talk about the second type of cyclone, which we are calling as tropical cyclones. Now, talking about tropical cyclones, what happens exactly in tropical cyclones? So tropical cyclone is a system of, again, low pressure, okay, which develops in the lower latitudes. And how it happens overall? So this cyclonic condition, when develops in the tropical regions, the primary idea, if we see overall mechanism of the tropical cyclone over here. So what happens in this case is, let's say, for example, I am taking large water body, oceans and all. Now, this is a tropical region. So we are talking about warm oceans. Warm oceans in general, I'm taking the temperature here to be greater than 26.5 degrees Celsius roughly. So this is the temperature of the ocean waters. Now, in this case, what would be happening? We are talking about a low pressure system created over the ocean. So when this low pressure system comes up, what will be happening? The air would be rushing inwards. Okay, low pressure pulls the air towards it. So in this case, the air rushes towards the low pressure. Now, air rushing towards the low pressure, it otherwise would have filled up the low pressure. But over here, again, the same idea, that is Coriolis force will work on it. And due to the Coriolis force, there would be deflection. Okay. Now, in this case of deflection, due to Coriolis force, what is the result? The result is air starts rotating around the low pressure in anti-clockwise direction. If I'm taking up northern hemisphere, if it is southern hemisphere, the air would be rotating clockwise. Yes. So now the air starts rotating around the low pressure. This is what has been seen in the temperate cyclone case also. But one additional thing would happen over here. This is a tropical cyclone developing in the tropical region, which means air here would be very warm. Okay. Now, two things are happening. Air is warm, and we know when the air is warm, air always rises. Warm air is lighter, so warm air rises. So in this case, there are two types of motions that the air would be exhibiting. First, that is, air would be rotating around the low pressure in anti-clockwise direction, and second, air would be rising, rotating and rising, which means overall, what would be the effective movement of the air if it is rotating as well as rising? It would be nothing but spiraling upwards, rotating and rising. So the air effectively would be moving like this. Air would be rising. Now, air rising, this air, rising air, will result in condensation, reaching the dew point. When the air would be rising, it is cooling, and eventually it will reach condensation point or dew point, from where it will start forming the clouds. Now, this air is very warm, have a lot of moisture, because it this whole system is developing over oceans. So if it is very warm, plus it has a very high amount of moisture, it will result in huge vertical or tower cloud formation. And we know this, these tower clouds we call as cumulonimbus clouds. So over here, tower clouds would be formed, and this would constitute cumulonimbus clouds. And from these cumulonimbus clouds, now it rains heavily over here. This is a general mechanism of a tropical cyclone. So in this mechanism of tropical cyclone, I'm repeating again what exactly is the scenario. You have a warm ocean water. On this, intense low pressure develops. Due to the intense low pressure, air converges in. But due to Coriolis force, it starts rotating. Now it rotates as well as it is warm air, so it rises. Rotation as well as rise results in the air spiraling upwards, and air rising up, it would become cold, reaches dew point, and condensation happens. And that results in formation of cumulonimbus clouds over here. Okay. Now in whole of this system, what happens is when the air rises and the air reaches a dew point, from where I'm saying cloud formation is beginning, condensation causes what? Condensation causes heating. Yes, we know this concept of latent heat of condensation. We have discussed already. And what has been established is latent heat of condensation is always released. So whenever condensation happens, okay, it heats the surrounding. And the surrounding here is air only. So just think of the scenario that air is rising. Air is rising, why? Because air is warm. But it is cooling eventually because of the rise. Reaches dew point. And now condensation happens. When the condensation happens over here, now the heat would be released. And this will warm the air more. Although reaching from here to here, it was cooled now, but it becomes warm again. And so starts rising far faster. It was rising normally, reaches here. By this time, it has become relatively colder. But then condensation again added the heat. So it again becomes heated. And so it further rises faster. When it rises faster, what will happen to low pressure here? Low pressure will become stronger. Rising air, low pressure. So the fast rising air results in strengthening of the low pressure, and this goes on strengthening the tropical cyclone. So one straightforward idea, if you are asked in the examination a direct question, that is the driving mechanism for a tropical cyclone. And the answer would be condensation. Because every time when condensation happens, and it is a continuous process, every time when condensation happens, now it heats up again the air, and so air rises fast, making the low pressure strong again. And so it goes on increasing the strength of the low pressure, in fact. So condensation is the driving mechanism behind tropical cyclone. Now, if you see, what we are talking about is the favorable conditions for the tropical cyclone. So the favorable conditions for the tropical cyclone, first I can say what I need is warm ocean waters. Yes, so now warm ocean waters, and this warm ocean water where we have established temperature to be somewhere greater than 26.5 degrees Celsius. Okay, in general in books you'll find it to be 27 rounded off. So 26.5 degrees Celsius to be very specific. Because if water is cold, evaporation would not be rapid. We need rapid evaporation so that air takes up a lot of moisture from the ocean. Second, for the rotation, you will need Coriolis force. Okay, yes. So Coriolis force would be required. In addition to that, now when we talk about this condensation happening and cumulonimbus cloud formation happening, all and all this is related to low pressure near the surface. Yes, you need a strong low pressure for whole of this system to happen. Okay, but now, if there is low pressure at the surface, effectively which pressure you will have on the top? It would be high pressure. Because if the air is converging over here, rising, so definitely air is going to diverge over here. So this low pressure would be very simply strengthened by the conditions of diversion of air in the upper troposphere. So if the air diverges in the upper troposphere, automatically it will strengthen the low pressure near the surface. And so what we would write over here under the conditions is the upper air divergence. Upper air divergence. And then lastly, what will be happening is, if you see whole of this system is blown by the winds. Okay, so winds, if I talk about the winds over here, so in this case, when the winds are blowing like this, it's very natural that as you go up the air, the speed of the wind will go on increasing. And why is it so? Because near the ground, you have very high level of friction from the ground. And as you move up, the friction goes on decreasing. Plus, in addition to that, the air is also becoming thinner. The density is decreasing. Because of these two reasons, air is also thin, friction is also not there. As you go up, the wind velocity goes on increasing. Okay. So when you talk about differences in the velocity, let's write it: velocity v1, velocity v2, velocity v3, velocity v4, velocity v5. This difference in the velocities, like v2 minus v1 or v3 minus v2, how much is the difference? This difference we call as wind shear. Wind shear. How much a difference is there? Now tell me, for this system to be stable, because this is a system involved with cumulonimbus cloud, which we know forms up to the height of 12, 13, 14 kilometers also. So if this is one such system extending up to 14 kilometers height, and if I want whole of the system to be stable, even if moving together, you will need less wind shear or more wind shear? Tell me please. Repeating again the question, if you want whole of the system to move together as one single system, not breaking up also, okay, you would need less or more wind shear? Yes, very good. Definitely less. No doubt in that, because if the wind shear is more, the upper air is moving very fast, it will take away the clouds. And so the system cannot sustain itself. So in that case, a very simple and straightforward condition I would write is less vertical wind shear. Okay. So under these conditions, a tropical cyclone can be formed and it can be sustained. Now in whole of this system, if we talk about the structure, how this tropical cyclone overall looks like. So in the case of the structure of tropical cyclone, you can see over here how and what happens. So first thing in this diagram, what you see is, when the air is converging in and rotating around the low pressure, air is not able to reach the central low pressure system. It is only rotating around it. So the central region which is there, this is a region where air is not reaching, and I'll shade it over here. In this case, we are talking about this region. okay, around which only the air is rotating. Okay, air is not reaching this region. And so you call it eye of cyclone, the central part of the cyclone, which is called as eye of cyclone. Yes, now in this case, the eye of the cyclone, overall, how it would be looking like now? So what we'll see again is the low pressure system over here. And what we have drawn is air converging in and starts spiraling upwards. This portion is what we are calling as eye, the central portion where the air is not reaching. So then this eye definitely would become a windless zone. Air is not reaching over here, it would be windless zone. Now surrounding the eye, the air, what is moving around, this is called as eye wall. Okay. Now when we see this eye wall, there would be a lot of air moving around. And so you have successive layers of air as you are moving out. And likewise, you call the first one as inner eye wall, this one outer eye wall, in the center you have eye, so eye, inner eye wall, intermediate eye wall, outer eye wall, and so on. My one question here would be, if I talk about eye wall, inner eye wall, outer eye wall, in which case I'll get more of the wind velocity? That is near the eye or away from the eye? Inner eye wall or outer eye wall? Okay, where I should get more of the wind velocity? So highest of the wind velocity, yes, very good, would be the inner eye wall, because its radius is less. Okay, so lesser radius, more velocity. Here you are using a law in physics called as the law of conservation of angular momentum. You're not required to know the law or anything. I'll just give you one or two examples so that you will figure out why it is happening with the examples that we were told in our school textbooks about the application of this law of angular momentum, conservation of angular momentum. Which one example was when an ice skater has to rotate fast, what do? Okay, they simply fold their hands like this. Okay, initially they are rotating like this and then they fold their hands. Folding the hands like this, the radius, effective radius decreases. And so automatically the rotation speed increases. Or a diver, when has to make more somersaults in the air before reaching the surface. Okay, they fold their body. So folding their body, rotational velocity increases. So this is how law of conservation of angular momentum is applied. And that's the same rule we would be using over here. Lesser the radius, more would be the wind velocity. Okay, so we have eye and eye wall. Then in addition to that, the other part of the structure of a tropical cyclone comprises of the cumulonimbus clouds, and then most importantly, when the rainfall happens, rainfall does not happen over a very large area throughout the clouds. No, rainfall here occurs like in one area it is happening, it will leave some area and then again rainfall will happen. And these regions, they are called as rain band. Okay, now rain band. What's this rain band? Why rain band? Why continuously the rainfall is not happening? Because what happens is when the air rises, a lot of air is rising, becoming cold. then the cold air has to come down also. This is whole of the rule. Warm air goes up, becomes cold, comes down. Goes up, comes down. But coming down, if this is a region which will be covering the area as large as a 50-60 kilometers diameter, where will the air descend? So air forces itself downwards within this system only. And wherever air is forcing itself downward, what I'll get is no cloud formation. So in this case, what we can draw like is the clouds now. I'm drawing like clouds have formed over here. Then clouds have formed over here. And in between that, you have this gap. Okay, although on the top portion, you'll find the clouds to be like this. So from here, the air forces itself downwards. Okay, and so this remains as a dry zone. Okay, yes, so we have these rain bands. So in the structure of cyclone, what are the different portions that we have? In the structure of the cyclone, we have eye, second eye wall, third cumulonimbus clouds, and fourth rain band. These are the parts of the structure. And so you can see it now very clearly over here, what exactly I have told you. In the center, you have eye. Okay, then you have eye wall, where the wind velocity is maximum. Then now you can see the rain bands. Yes, so 1, 2, 3. These are the rain bands. And between that, you can see the space which is there where cloud has not been formed. Although on the upper part, there is a flow of air taking place. And along these, you can see in the blue arrows, the descending air. Plus, because I is again a region where no wind, no rise of air is taking place, or some air find its way down here also. And so you have the cyclone, structure of cyclone looking like this. Okay, yes, everyone. So now, if I ask you, and this is a question which has been asked in the examination repeatedly, that is the characteristics of I. What are the characteristics we can associate with I? So just try to figure out in terms of wind velocity or in terms of pressure or the movement of air. How exactly and what would be happening? Yes, people, give me the answer. How and what would be happening? Yes, please. What about the pressure? Tell me first thing. What about the pressure? What would be the pressure here, high or low in the eye? Okay, first property, lowest pressure for sure. Second thing, tell me now, wind velocity, what about it? Wind velocity. Windless. Third property, cloud or cloudless? Cloud or cloudless? Since there is no rise of air, there is no question of formation of clouds. So this becomes cloudless zone. Okay, fourth property, zone of ascending or descending air? Zone of ascending or descending air? Zone of descending air. Cold air descends from here as well as between the rain bands. Yes, so this is the mechanism and the structure of a tropical cyclone, how it happens. Okay, so overall now, let's figure out this whole phenomena, how it occurs. So let's see this phenomena.
There are three basic stages in the life of a tropical cyclone: its origin or source, mature stage, and the dissipation stage where it died. These occur in a continuous process, not as separate and distinct stages. Each stage may occur more than once during the life cycle as the strength of the cyclone rises and falls. It may reach land, weaken, then go back out to sea where it strengthens once more. The formation of a cyclone depends upon the following conditions coinciding: a large, still and warm ocean area with a surface temperature that exceeds 26.5 degrees Celsius over an extended period. This allows a body of warm air to develop above the ocean's surface. Low altitude winds are also needed to form a tropical cyclone. As air warms over the ocean, it expands, becomes lighter, and rises. Other local winds blow in to replace the air that has risen, and this air is also warmed and rises. The rising air contains huge amounts of moisture evaporated from the ocean's surface. As it rises, it cools, condensing to form huge clouds about 10 kilometers up in the troposphere. More warm air rushes in and rises, drawn by the draft above. The rising drafts of air carry moisture high into the atmosphere, so that these clouds eventually become very thick and heavy. Condensation then releases the latent heat energy stored in the water vapor, providing the cyclone with more power. This creates a self-sustaining heat cycle. Drawn further upwards by the new release of energy, the clouds can grow to 12 to 15 kilometers high. The force created by the Earth's rotation on a tilted axis, the Coriolis effect, causes rising currents of air to spiral around the center of the tropical cyclone. It is at this stage that the cyclone matures and the eye of the storm is created. As the air rises and cools, some of this dense air descends to form the clear, still eye as the cyclone rages around it. The eye wall, where the wind is strongest, behaves like a whirling cylinder. Cyclones rotate clockwise in the southern hemisphere, anti-clockwise in the northern. The lowest air pressure in a tropical cyclone is always found at the center and is typically 950 millibars or less. The average air pressure at the Earth's surface is about 1010 millibars. Tropical cyclones have significantly lower air pressure than the air that surrounds them. The bigger the pressure difference, the stronger the wind force. One of the lowest air pressures ever recorded was 877 millibars for Typhoon Ida, which hit the Philippines in 1958, where winds reached 300 kilometers an hour.
Okay, yes, everyone understood what in general has been given about the tropical cyclone, the same mechanism and structure that we have studied. Okay, so in this case now, this is what we are calling as tropical cyclone system with all its structure. Now in this case, so what has been established is the eye which is there, has the lowest pressure and all. So let's observe how exactly eye and eye wall works. Okay, so again what we are doing is, let's observe the wind systems on the Earth in a live mode. Now this what I have, I'm showing you, this is a live feed. This is a live feed as of now. What are the different systems of cyclones happening where? Okay, so in this case, let's figure out, let's check in northern hemisphere if there is any cyclonic conditions anywhere. And so one cyclonic condition, anti-clockwise rotation of the air, you can see in northern hemisphere. You will be witnessing something over here in this range. Okay, so this is a cyclonic system. And with this cyclonic system, what we can figure out is the center. So at the center, just check on the left side, the wind speed. Wind speed has been given as 32 kilometers per hour. Okay, in the central portion where I have marked it. Okay, if I take the point a little bit further apart, now you can see 76 kilometers per hour. Okay, and then again moving towards outer eye wall, the wind velocity further start decreasing, 61 and 44 and so on. But right there in the middle, you can see the wind velocity. This is the eye, okay, where the wind velocity is extremely less. Okay, in fact, since this is not a fully developed cyclone as of now, okay, because at any point of time, I'll not find a fully developed cyclone anywhere in the world necessarily. So this is a one cyclonic condition in a development. And so over here, what you see is the eye, and this is how it will work. Similarly, in the other parts, say for example, if I move to southern hemisphere, I'll have to look at the clockwise movement. Okay, but these clockwise movements, what you are seeing, they rather are in the temperate zone. Just let's check in any other portion if I have these cyclonic conditions where we can see the velocity. Okay, so one we can see near North America. And just let's check the wind velocity so that we'll get an idea of whether, so in the eye, I have the wind velocity 40 kilometers per hour, and just moving out. Yes, now this you can see is a much more developed cyclone, wherein the inner eye wall has a wind velocity of 133 kilometers per hour. And so 133, yes. And as I move out towards the outer eye wall, the wind velocity is decreasing.